Direction. So today I will speak about this Eigenstate thermalization hypothesis. So basically it's an idea to explain the quantum statistical mechanics. So it's a fundamental in nature. So it's basically an ansatz to explain how the isolated quantum many-body systems come to equilibrium after some time. Means whether or not the system is going to equilibrium or not. That's the theme of the talk. So basically it's an ansatz to understand the isolated quantum many-body system, how it comes to equilibrium. That's the main theme of the talk. So before it's the proceeding, so these are the two fundamental pillars of the famous successful theories of physics. So on the one hand we have quantum mechanics, and on the other hand we have statistical mechanics. So when we talk about the quantum mechanics, so you have a system, means the system is interacting with so many degrees of freedom, and so it's about describing the physics in the microscopic level, basically the physics for atoms, molecules and ions and photons. So for describing these things in quantum mechanics, so you need some function called a wave function. It's a vector in the Hilbert space. So it's evolved under the evolution of the famous Schrodinger equation. So it's a unitary kind of evolution. So that what I mean by unitary kind of evolution means if you prepare the system initially and you evolve the system with respect to your Hamiltonian, you will end up with another state which is time dependent, but that state it's encoded all the informations about the initial state of the system. So that's what I mean by unitary in the sense. So the quantum in the microscopic physics, so finally the wave function it's encoded all the informations about the initial states. So that's the thing in the quantum mechanics. But if you look at the same thing in the statistical mechanics, it's also for the microscopic world. But the things are weird in that sense, means you are not applying that physics for a single particles, you are applying the physics for a bulk number of particles, maybe n tending to infinity in the thermodynamic limit. So this is the physics basically explained for phase transition, thermodynamics and stuff like that, and you will apply your microscopic physics to the particles, and finally you come out of some macroscopic variables like entropy, energy and all stuff like that. So here the basic thing is you have to, when you reach the equilibrium, you basically maximize your entropy. And the thing is like unlike in the quantum mechanics, the things are here it's irreversible in the sense that if you start with a system and eventually it will come to equilibrium after some time according to the basic principles of equilibrium statistical mechanics. So the system will eventually come to an equilibrium. So that state is maximum entropy states and you cannot go back to the initial states. But that thing is available with the unitary transformations in the quantum mechanics. So in this sense, there is naively some contradictions are here with quantum mechanics and statistical mechanics in the naive way. So the contradictions are not profound. On the one hand it's a unitary evolution, on the other hand it's an irreversibility. So today I am talking about how these things are rectified at least for some of the systems, not for the every system. So that means by every system that not thermalizing. So if you have a system and you evolve the system with respect to some Hamiltonian, the system will go to all the available spaces in the phase space according to the classical mechanics. So that's the thing. So it visit all the spaces in the phase space and eventually it will come to an equilibrium, means there is a temperature between the system and surroundings. It's same for the system and its surroundings. Here it's called the bath or some kind of heat reservoir. So whatever the leftovers in the system, it will dump the system into its bath. So the system will finally or eventually give some distribution function, it's called the rho, and all the macroscopic variables, you can find it out with respect to this rho. That's the thing. So you start from here in the phase space and you evolve the system with respect to some Hamiltonian, whether what I am talking right now is in the classical sense. So the system will eventually go to all the equal available spaces in the phase space and according to ergodicity. So the ergodicity is the main hypothesis in this statistical mechanics. So ergodicity, what it's mean by is like so you have a system and you weight the system for t tending to some infinity, means you weight the system to thermalize for at least for some infinite time. So what happens is like the system will visit all these spaces and it's eventually come to equilibrium. That's the scenario we are always taken in the equilibrium statistical mechanics. So always there is a thermalization in the equilibrium statistical mechanics, whether it's a classical or quantum sense. So these two are the main, what I mean by thermalization is the system and the surroundings come to a common temperature which shares something between the system and surroundings. Even though the system has so many other degrees of freedom, it's only after the equilibrium or when the system is reaching the equilibrium, it's only talking to the subsystem or the surroundings with very few degrees of freedom. So that's what I mean by the thermalization. So things are looking.
The system, you assume the system to be a mini-body system.
Yes, that's what the thing. So you cannot simulate the single particle system with a Hamiltonian.
You are talking about equilibrium of the mini-body system.
Not the single system. There are n. That's what I am saying. I am talking about the thermodynamic limit, the n tending to infinity limit, not about the single particle system. So single particle system, it cannot go to equilibrium. That's the thing. So these are the type of thermalization while we are studying statistical mechanics. So one is the thermalization in open system. So it's very clear, means when you consider an open system, so you have a system, then it's surrounded by some kind of bar, and the system and the surrounding is exchanging energy with respect to energy, and they will eventually come to a temperature which is embedded in this beta factor, and you can probably you can get all these microscopic variables with respect to these partition functions in the open system. So things are very well and good in open systems, but the complications happen for the closed system. So you have a system which is closed completely, means there is no talking between the system and the surroundings. So there you have this microcanonical ensemble for describing the system in the closed sense. So basically you can get a probability density and you maximize this probability density. Eventually the system will goes to equilibrium, and that means that this entropy, this is the main thing in the closed system. So the available microstates is proportional to the entropy of the system. So it's maximizing. So things are very well and good in classical sense. So this is what I mean by the classical thermodynamics. So means classical thermalization. So there is the chaos is making a role here, means in the classical sense, because suppose if you consider a dilute gas in a box or something and you evolve the system, consider the gas is classical in sense. So chaos play a role here, and eventually the system will come to equilibrium. So the thing is like the classical systems with chaotic behaviors, it never goes to thermalize. So the one exception for this scenario is the Fermat-Pasta-Ulam problem. So there, even though you have a unharmonicity in the system, but the system not go to equilibrium. So the equilibrium, the thermalization is somewhat tricky. So that means like in certain systems it will go to thermal equilibrium, in some cases it's never go to equilibrium. So the system will localize itself. So the thermalization means in the language of quantum mechanics means the system will eventually go to some states, it's called a mixed state. Okay, it's in the local sense, means globally the total system is in some kind of pure states, but you look the subsystem of the main system, so it's locally it will thermalizes with its subsystem. That's the big idea. Here the Hamiltonian is it's a combination of momentas and coordinates.
Those independent variables become time dependent. That means it indicates the non-equilibrium.
That's what the system will start from out of the equilibrium. It evolves for some time, and eventually it will go to equilibrium. That's what.
Once it takes up equilibrium, then it becomes time independent.
Yes.
Then that Q and T, that independent variables are shown to be functions of time.
Initially it's a functions of time, but eventually those numbers.
It becomes independent.
Yeah, independent of time. That means that when the system is come to equilibrium, the microscopic physics is disappearing from the system, or we can say that there is a information is somewhat lost from the system. Lost means it's not actually missing from the system. It's some kind of misplacing the information. Misplacing the information, what I mean is like you cannot measure it experimentally. So that's what I mean by the system is thermalizing. So some way whatever the informations in the system is losing. Not losing means in that sense it's misplacing the informations. That's what I mean by losing. So those things are very well good, and in classical sense means we have ergodicity and Boltzmann-X theorem and equal probability, equipartition theorem. All those things will eventually come the system into thermal equilibrium, at least in the sense of when t tending to infinity limit. So how and why these things? So when we map these things into the quantum cases, the problem arises. So the mapping is not such simple way. So the problem arising is like where the quantum systems are usually defined by these unitary evolutions of the Schrodinger equation. So the unitary evolution will tell you us that if you have a system at t is equal to 0, means initially you prepare a system, okay, you evolve the system with the now onwards I will talk about in the quantum language, means I switch to the quantum state. So the Hamiltonian we are using is the quantum Hamiltonian. So I allow the system from initial state to some final state using this quantum Hamiltonian, and so initial state is some kind of a pure state, means the system is completely isolated in the sense that there is no entropies associated with the system. The system is pure in that sense. Wait for some time, okay. Eventually the system will go to equilibrium. That's the tricky part. Sometimes it can go to equilibrium, sometimes it never go to equilibrium. It depends on the system's Hamiltonian. So if it goes to equilibrium, so it's finally whatever the values, whatever the expectation values you are getting from the quantum mechanics is matches with whatever the quantities you are using to get from, supposed to get from the microcanonical ensemble. So these two things will match. So why it's so important? Because of these following reasons. There are these, if you look at archives on a daily basis, you can find it out 2 or 3 papers. It's about this ETH. So it's a hot topic in current research. So there are so many numerical simulations, hexadiagonalizations, and ultra cold atoms experiments and superqubits. So this thermalization business is, it's a vast range of, it's an area. So it's ranging from some black hole physics to come down to the quantum computation level. So that's why this topic is so much important. So everyone is trying to prepare something isolatedly. That's what the main reason why we are studying this thing. So first of this kind was first observed by Anderson for his studying some spin lattice glasses and stuff like that. So he put some random EQs, so randomness into the Hamiltonian, and he find out that the system is not thermalizing, means it's called the Anderson localization. So this is the starting point of the problem, and the big question we are actually asking is what is this mean by this thermal equilibrium, at least in the case of quantum systems, and because we are studying about isolated many bodies strongly interacting quantum systems. So before this thing, these are some assumptions. So you have to take your quantum degrees of freedom interactions are in short range in real space. It's a non-relativistic in nature, and the system is fully isolated. There is no heat bath is associated. So this is basically a typical isolated quantum many body system. So these are the spin degrees of freedom. So it's constantly interacting with its neighboring through some kind of interactions, and we are only interested in some high excited state, not the ground state. So that means there is no quasi-particles associated with these things, and so these are the some assumptions before we start the proceedings. So you have a pure state, you can assign a pure state, initial pure states to the whole system, and the Hamiltonian is some maybe the interaction between these two things. So you evolve this state with respect to this Hamiltonian under these unitary transformations. So these things are means it's not stationary in the sense, means it's not dynamic, but eventually after some time, maybe some t tending to infinity, means some infinite time, the system will come eventually to a state which is described by this one. So it resembles to a mixed state. So this is a pure state, and the system will eventually come to a mixed state. So mixed state means it has some maximum entropy, so because the system is reaching the equilibrium. So that's the thing. So to understand this thing, we need some knowledge about this quantum entanglement business. So this is our total isolated many body quantum system in some state psi, initial state. So what I consider is like inside the system there are so many subsystems. So whatever the things, so that's what I mean by locally and globally. So globally it's in a pure state, it's represented by some psi or whatever the states, but locally these things, means whatever the subsystem, I call the subsystem as A, and the rest of the part I will call it as B. So this is the system, and this is a kind of a heat bath to this system. So after some time locally this A will come to equilibrium with these things through entanglement. So entanglement is playing a big role in thermalizing these quantum many body systems when we are talking about isolated many bodies. So these are some protocols you have to follow to find out this this entropy. So the entropy hereafter, what I mean by is the entropy of the Foy-Neumann. So it's basically the entanglement entropy between the subsystem A and B. So finally if the system is coming to thermal equilibrium, so then that time locally this entanglement entropy becomes the thermal entropy. So that's the big deal here. So here what happens is like the subsystem will, or the system itself will act as a heat bath to its subsystem. That's the big story for the case of quantum many body interacting system. So this is what, if the full system is not thermalizing, because the full system is in a pure state, that means that you cannot use this canonical kind of stuff for the density matrices, but only subsystem is thermalizing. So for the subsystem means locally, so I have to put locally, it's go to the thermal entropy thing, means both the entropy or the reduced density matrix of the subsystem is same as the total density matrix of a full system, means this looks like a thermal density matrix. So only the subsystem density matrix is locally will look like its thermal density, which only depends on few parameters in the system, means either it's a temperature or a chemical potential or energy of the system, means the system has only few conservation quantities available in the system. So this is the thing. So you have a system, and you initially it's in some initial states EI, and I evolve the system with respect to the Hamiltonian H. So you eventually you can use your Schrodinger equation. So you can write your final wave function something like this, and you find the expectation value of this sum of the observables, maybe total energy or something of the subsystem, and you time average that system. It eventually will give this number. But the problem here is these CIs, whatever the coefficients inside this full wave function, it's a time, it's remembering its initial state. That's the problem. Because when you reaching the thermal equilibrium, the system will lose all the informations about from where it coming. But here, always in this case of quantum mechanics, so you have a quantity, this coefficients, it always depends on the or highly it's sensitive to the initial condition. So that's the thing. So this is what we do some. So we do it in quantum mechanics. You find the expectation value of some observables with respect to this wave function. So you have two parts. One part is something like this and another part is something like, so it's a kind of a interference term because it contains some difference between the energies, something like that. So the big deal is if someone is going and compute this sum of the observable with respect to this wave function, so you will get two pieces. One piece which is quite similar to what the piece we are supposed to get from the microcanonical case, and another piece, this is some kind of a fluctuations. So if the system is coming to thermal equilibrium, means these fluctuations will eventually goes to zero when you, at least when you take the thermodynamic limit, and these expectation values we compute from using quantum mechanics, and which exactly similar to what we are supposed to get from the microcanonical state. So people call this is some kind of an ansatz to say whether or not the quantum many body systems is thermalizing. So the ansatz is, this is the ansatz. So you have an operator which you supposed to compute is expectation value. So you get two pieces. One piece is which is quite similar to what is supposed to get from the microcanonical case, and another piece which is always time dependent piece. It's kind of a fluctuation piece. So this piece they compute finally, it's we can relate this thing to some entropy. Entropy means the Feynman entropy, and this is some factors which is random in nature, and this is another function. So this is called the Eigenstate thermalization hypothesis. So the big deal is if a system, if someone is saying that my quantum mechanical isolated many body system is it's thermalizing, that means that you have only this piece. If it's not thermalizing, you also have this piece, and the contribution from this piece is too high, means the fluctuations are too high. So that's the big deal. So it's a kind of reinterpreting the Ergodi hypothesis. So instead of Ergodi hypothesis in the usual classical statistical mechanics, so you have another ansatz whether or not the quantum many body systems are thermalizing. So this ansatz is it's called the Eigenstate thermalization. So the take home message is if this part is too high, the system is never thermalized. If this part is too high compared to this one, then the system will thermalize. That's a big deal. So these are the work for it's first done by Deutsch he wrote a paper in PRA and followed by Shetnicki, and there are a number of papers available in the net for using different to understand different kinds of systems. So this is the story of the Eigenstate thermalization. So it's kind of understanding your quantum many body systems using your quantum mechanics. So you have an extra piece while you studying this. So that piece is called Eigenstate thermalization. So it's similar to what the ergodicity hypothesis in the usual classical statistical mechanics. So
can we say that the hypothesis amounts to identifying two pieces, one as the usual classical like and matter, with the sum of two quantum mechanics?
that's what I am saying. Someday, see, we don't know which kind of systems are thermalizing. Only we have some vague idea like only the integrable systems are not thermalizing. If the system contains too many anharmonic terms in the system, it eventually will go to thermal equilibrium. That's the story. But I cannot say that all the systems will follow this Eigenstate thermalization hypothesis and it's finally will say come to equilibrium.
May or may not?
Yeah, the may or may not. That's the thing. Because if you consider the Fermi-Pasta-Olam rule, that's a classical problem. Usually according to the usual classical statistical mechanics, the system will eventually come to the equilibrium, but in the case of that thing, because the system contains too many unharmonic terms in the Fermi-Coulomb past the rule, that system will never thermalize. It's localizing, means it's come to its initial states finally. So that's the paradox to this normal statistical, means the ergodic hypothesis. So I cannot say that every system will come to equilibrium. There are some systems, if the integral motions or some conserved quantities are less in the system, that kind of systems will eventually go to thermal equilibrium.
And the system, do you assume that the system consists of several subsystems?
Yeah, I am, but that's why I am saying I am considering a too many system, means degrees of freedom. They are continuously talking to each other locally, means not, they are short range interval.
As a whole, doesn't it?
As a whole it doesn't, because it's in a pure state only. That's what I am saying. Globally it's in a pure state, it's never go to equilibrium, but locally it's kind of a talking to each other, and some part will act as a bath to the other part. So that's the thing. So that's why, so even the single eigenstate will act as a microcanonical ensemble using this and such. So that's what I mean is like when we studying statistical mechanics, so you have a microcanonical ensemble. So there you, even though the microcanonical ensemble there is nothing is exchanging with its bath, but for deriving some properties we have to take some energy difference, means some distribution functions between some energy epsilon and some nearby energy epsilon plus delta epsilon, and from there we are finding out what is the phase volume between that energy window. So in that same sense here, when the system is reaching the equilibrium, even the single eigenstate will mimic as a microcanonical ensemble, means using a single eigenstate you can extract all the informations about the macroscopic world. That's the big deal. So the thing is like when if you look at the classical thing, you narrow down that energy window, means you can find it out only one eigenstate. So that's the thing between, that's a comparison between the classical and the quantum cases. So finally you have this phenomenon entropy. Usually it's an area law, that's why it's people will connect this thing to black hole thing, but for high energy states it's obey the volume law, means it's an extensive parameter when the system is thermalizing. So that's the thing. So this is the conclusion, means some take home messages. The quantum thermalization is some kind of equivalence between the time evolved pure states and the thermal states. It's only an answer, there is no concrete analytical proof, only the numerical studies are there, and it's well good with systems. So this is the thing. So for a long time period, when you compute this expectation value, it will eventually go to your microcanonical expectations value. That's the sufficient condition for getting quantum thermalization. So these are some of the real experimental things, and this is done by the Block group in 2012 or something. So they did some ultra cold, these are some fine tuning experiments. It's a highly sensitive experiment, means a lot of precautions are there. So this is basically your initial state, and you hold the state with respect to this Bose-Hubbard model, and eventually it will come to an equilibrium. So initially it's fluctuating, that means that other piece, the off diagonal piece, has more contributions. When the time goes, it's finally reaching some equilibrium after some 20 milliseconds or something like that. So this is the real thing happened in real systems, and this is the another experiment from another group. So they all find it out that initially even though the system is pure, finally, means when the system is completely isolated and evolved with some kind of Hamiltonian or conjuging something, so eventually you will get volume law. Initially you have a means some kind of area law, but for higher states, for the thermal states, if the system is thermalizing, you will get this straight line. This is the graph for Rayleigh entropy versus area. This is the Another thing, it's a Newton's quantum cradle experiment. So this violates the ETH, means it's never will go to equilibrium. The system is highly localized one. It's not thermalizing. So this is the thing. So this is the comparison between the classical and the quantum cases. So in the classical system, you have an initial state, and you try to evolve the initial states with some Hamiltonian. So it go to all the spaces in the phase space, and eventually it will come to thermal equilibrium for a very large, after a very large time. But the things are not looking good in quantum systems. Some quantum many-body systems that will go to thermal states, but many of the quantum isolated systems are never go to thermal equilibrium, means that fluctuations are too much high in some cases. So we don't know how to tackle that situation. Only we have some numerical this thing. So the thing is like, so when we study statistical mechanics, we will say that we have a cup of tea, and we will try to kept it on a table, and we kept it on a table. Eventually the coffee will come to equilibrium with its surroundings, but the situations are quite different. If you isolate this coffee with some wall or something like that, and you assume your coffee is quantum in nature, means the particles are evolve under some kind of quantum Hamiltonians, nobody knows whether it's come to equilibrium or we can drink the coffee, means we don't know. That's the story. Some systems may thermalize. If it's thermalized, it will obey the ETH and such. But if it's not thermalizing, it's never obey ETH. So we don't know how to quantify those thermalizations. So that's the thing. So thanks.